So welcome everybody. Welcome to Hugo's talk on Dask DataFrame Groupby. Why can it fail and how to compensate? Let's
Okay,
jump in, Hugo.
can everyone see my screen?
Yes, we can.
Okay, I'm going to try to take questions as they come in, but that may not work well, but we'll see. So if you do have questions, go ahead and please type them into the Q&A thing, and if I see them, I'll try to answer. Okay, great. So I wanted to talk about Dask DataFrame Groupby, why it can fail and how to compensate. And so before we begin, I just wanted to give a little background for why I'm giving this talk. I'm at Saturn. We have a data science platform that manages Jupyter instances, Dask clusters, and enables data scientists to deploy dashboards, models, and data pipelines. In a lot of our work, we're working with clients that want to load large data sets into Dask DataFrames, and oftentimes they run into trouble trying to do group bys. And so in a lot of the experience that we've had helping data scientists troubleshoot these issues, I wanted to sort of present some of the things that we've learned so that overall we can sort of improve how we are working with group bys in general. So to get into that, we have to start with talking about the different types of group by operations. So there are three types, and we're going to talk about this from the pandas perspective first, because the Dask DataFrame group by is based off of the pandas DataFrame group by. Pandas group bys have three types. There are aggregations, there are transformations, and they are applies. And I'll go through what those mean. So in an aggregation, data from each group is collapsed into a single row. So, and just a little, in this talk, I'm going to be using a synthetic data set that I created, a very small one. But there are three columns. There's animals, there's scores, and then there's a date. So when you see animals and scores, this is like from the synthetic data set that we're going to be using for the sample in all of these in this entire talk. Common aggregations that you'll see are sums, computing the variance, the standard deviation, and the mean. Transforms are operations that are executed on the entire group, but instead of reducing it down to a single row, it actually preserves all values, or all rows. So for example, in this case, instead of computing an aggregate statistic on the scores of a given animal, you can rank them, right? You can sort them into the, which one's the first biggest, second biggest, third biggest, fourth biggest, etc. And then finally, there's the apply, right? The apply is the most general. Anything goes here. The example that I'm giving here is something that sorts by the score and then returns the top three values. This is not an aggregation because you don't end up with one row. It's not a transform because no matter how big your group is, you end up with at most 3 rows. So why does this matter for pandas? In pandas, aggregations are fast because you know that every group is going to be reduced to a single row. And as a result, you can pre-allocate your result, right? If you know there are 50 groups, your result's going to have 50 rows. In pandas, transforms are fast because you know that each group is going to not change the number of rows that went in. So the result is going to be the same size as the data set that you started with. So again, you can pre-allocate. With applies, you have no idea because the arbitrary function that's passed in can do whatever it wants. And that's why they're slow. So why does this matter for Dask? So for Dask, it matters in a different way because things like pre-allocating memory is a lot less important for a distributed system. But the operations are still very different. So transform and apply both require access to the entire group's worth of data in memory. As a result, the Dask implementations of group by and transform and group by apply are very similar. Essentially, if your data has been sorted and Dask knows the boundaries of every partition in a Dask data frame, then it can be implemented just by mapping the operation onto every partition. Aggregations are different in that they're reductions. And so they can often be applied to different chunks of data. And we'll go through exactly what that means, but a high-level explanation is that if you think about computing sums, you can compute sums for different parts of your data, and then you can sum the sums, and then you can sum those sums, and eventually you'll get the sum for whatever you started out with. And I guess maybe before I proceed, I should give a little bit of background. I'm not sure how familiar people are with Dask DataFrames, but Dask DataFrames have an API that looks like a Pandas data frame, but underneath you have smaller Pandas data frames that we refer to as the partitions of the Dask data frame. So when I talk about partitions, I'm talking about an individual Pandas data frame, many of which will make up a Dask data frame. So we're going to start with aggregations and then talk about what you can do when your aggregations fail. And then we're going to talk about applies and talk about what you can do when the applies fail. So in Dask, aggregation operations are broken up into a chunk, a combine, and an aggregate step. The computation is broken up into 3 phases. And just one note, Dask has a function called apply concat apply, or ACA for short, that is used to implement a lot of the operations. In this talk, when I talk about aggregations, I'm going to be using terminology that's closely associated with the ACA algorithm. Dask also has a way to define custom group by algorithms, and it uses slightly different terminology. I'm not going to use that terminology. The first step of a Dask DataFrame group by is the chunk step, and the chunk is a function that executes on every input partition. So if my data frame has 10 partitions, the chunk step gets executed on each partition. Then the results of those the chunk step are combined in multiple stages, and then finally they're aggregated to produce the results. So that all sounds very abstract. Let's go into a concrete example. In subsequent slides, I'm going to have images of group by operations and tables that represent the data flow. Eventually, the graphs get complicated and the font size gets very small. I apologize, but I have no other way to represent the information. So hopefully it's okay. I will try to talk through it so that people with smaller screens will still be able to understand what's going on. So as mentioned, we have this synthetic data set that I made up. There are animals, there are scores, and there are dates. We're not going to do anything with the dates. They're just there to, show to have some more columns that we're going to filter by. In this case, I have divided the data set into 4 partitions, right? So there's one data frame for the month of April, one data frame for June, one data frame for May, and one data frame for July. The first step is the chunk step, which applies a function to every partition. In implementing this operation, which is just a group by a sum, every stage is going to look the same. Every stage is grouping by animals and summing the scores. Not all aggregations use the same operation at every step. Sums are very simple because you can sort of just keep summing and summing and summing until you get the final result. So the first step is to apply grouping by animals, summing by scores to every partition. And you can see that we go from 8 rows to 4, right? So we started off with 4 partitions of 8 rows each, and we ended up with 4 partitions of 4 rows each. Then those 4 data frames are concatenated into one big data frame, and then we run that operation again, grouping by animals and summing the score, and then we end up with the result. So this is a simple case where we are only using 2 stages, chunk step and the aggregate step. There's no combining here. And let's talk about some of the implications of this. So the chunk step reduces the data volume. We went from 8 to 4. You can imagine that there are probably other cases where your data is different or bigger, where the chunk step may provide a lot more reduction. So the fact that the chunk step reduces data is great, right? Because that means that subsequent steps have to deal with less data. The downside, however, is that all the data ends up in one partition. And this can be bad. I say can be bad because a lot of aggregations are massive reductions on data. And this approach of putting your results in one partition is oftentimes the easiest way to do it, and is oftentimes the right solution. It's oftentimes very fast. But what happens if I have like 1 billion animals, right? Then the result is going to have 1 billion rows in it, and that may not fit in memory. So Dask aggregations have a parameter called split out. And in this case, I'm saying split out is 4, meaning that I'm going to produce, instead of 1 partition, I'm going to produce 4 partitions. And so let's walk through this computation. The chunk step is the same, but now instead of concatenating all that data and then aggregating it, I'm going to split it out into groups. So you can see that I go from 4 data frames here to 16 data frames here. And each data frame in step 1 has 4 animals in it. And as a result, they each get split into 4 separate data frames for a total of 16 data frames. I also want to make another note that this is an overly simplistic example. In reality, you're not always going to have 1 animal in every group at the split out step, right? If I had 100 animals and split out was set to 4, I would probably have around 25 animals in every split. Now that I've got these 16 data frames, we then start concatenating them. But we don't concatenate them all together. We know that we want our results to have 4 partitions. That's why there are 4 data frames from each of the initial partitions. And so we collapse all the lynxes into the first data frame, all the alpacas into the second data frame, then the cats, and then the dogs. This sort of organizes the data such that all data for a single animal is in a single data frame in memory. And finally, we execute the group by operation, right? Grouping by animals, summing by scores, and that leads us to 4 data frames that make up the final result. So some comments on that. Now the data ends up in 4 partitions, which is good. But what you'll notice is that in this concatenation, we had data from every single partition flowing into the same data frame. What happens if I had 1 million partitions? So Dask has another parameter called split every, which defaults to 8, and that's a pretty good number. You're probably not going to have to change that, but I've set it to 2 just so that we can like see what it does on a smaller data set. So again, up to step 2, the split out is the same. We have 16 data frames, but instead of collapsing them in 4 at a time, since split every is set to 2, we collapse them in 2 at a time. So we've got 2 lynxes, 2 alpacas, 2 cats, 2 dogs, 2 dogs. Then we combine them, grouping by animals, summing by scores, and we have 8 data frames. Then we combine them again, 2 at a time, and then we aggregate them, grouping by animals, summing by scores, right? So split every allows you to take that single step reduction and break it up into multiple steps. So if you have a problem with the group by and an aggregate, what can you do? So the first thing that you should do is tune split out. And you can generally do this by thinking about what your data looks like. Or you can sort of run some experiments to understand what your data looks like in order to figure out what split out should be. In general, like targeting 100 megabyte partitions is a good thing. If I know that my data set has 10 million animals in it, and I know that a result with 1,000 animals is 100 megabytes, then I can 10 million divided by 100 will tell me what my split out parameter should be, right? So just look at how many animals you have, look at a sample of your data to figure out like how much memory each group is going to take, and then calculate how many partitions your result should end up in. And then you can that's a good starting point for experimentation. Alternatively, if your data is already sorted with an index matching one of your group by fields, you can use map partitions. So I know that sounds very complicated, but what this really means is that in a group by operation, you are collecting data for a single group, and then you're applying an operation to it. All these complicated steps are necessary when you need to move data across partitions in order to put them all in the same place. But if your data is already sorted such that each partition already has, like if my data frames already had all the alpacas and all the lynxes and all the cats and all the dogs in them, I wouldn't need to do this complex pipeline. I can just compute summing by animals, grouping by animals, summing by scores on every single partition, and my result will be correct. If your data is sorted, it can be tempting to just say, well, I can just use group by and apply. The reason why that's tempting is because Dask group by aggregations currently don't take any advantage of knowing that your index is sorted. Grouping by and applying does, so group by and apply will be implemented as a map partition if your data is already sorted. But I'm going to tell you not to do that and to use map partitions instead, because group by apply will use pandas group by apply, and that's oftentimes really slow. So a lot of times, I mean, these are all trade-offs, but in many situations, the computational overhead of the pandas group by apply when you're actually doing aggregation may be bigger than the benefit that you get from not doing this like cascading combination. Finally, I would say, like, given the choice, if your data is not sorted, don't sort your data just to implement the aggregation. You're probably better off doing things like tuning split out. And the reason is, if you look at this pipeline, there are reductions at every step of the way. And so the amount of data being transferred is much less than your overall data set because you're reducing it every step. Whereas if you go, I'm going to sort my data just to implement this operation, you end up having to move data around, but you're moving data around without the benefit of doing any of the reductions. And so that's most of the time way less efficient. I'm going to say this multiple times during this talk, but it is generally great if you can have your data in your data store or wherever it is, sorted in a way that matches with how you're going to use it. Whenever you can do this, you should do that. Okay, so let's go to applies. So I'm going to walk through what the implementation of a group by and apply looks like. Unfortunately, there's a lot less that you can do with applies, but we'll talk about that. So I'm gonna do the same thing that we did, grouping by animals, summing by scores, but I'm gonna implement it as a group by apply. In Dask, the way that this works is if your data is not sorted, the data is shuffled so that all the data for a single group is in one partition, and then pandas is used to apply your function. The shuffle is unneeded if your data is sorted. And for Dask, that means your data frame has an index, and that index has known divisions, meaning Dask knows that the maximum and minimum values of your index for every partition in the Dask data frame. And this will happen if you call set index on your data frame. Okay, so again, we have 4 partitions of data. The first step in the shuffle is to split them out. So I go from 4 data frames to 16, where each data frame with 4 animals goes to 4 data frames, which each have 1 animal each. Then all like animals are concatenated. So I end up with 4 data frames with all the lynxes, alpacas, cats, and dogs. And finally, I group by the animal and some scores to end up with 4 resulting partitions. What you'll notice is that at a minimum, we created n by m tasks where n and m are the number of input and output partitions. So in this case, this was the 16, right? There's 16 data frames here. If n and m are large, that's not great. So as a result, Dask does have a multi-step shuffle. And so normally that parameter defaults to 32. So if there are more than 32 splits, then it starts to do it in multiple stages. I don't actually think you can change that parameter, but I hard-coded it to 2 for this example to see how it functioned. So you can see that we start with, again, the 4 data frames, but instead of splitting it out to 16, we split it out to 8. So each data frame goes to 2. This one has links in alpaca and then cats and dogs, links in alpaca and then cats and dogs. Then we concatenate them, and then we do it again. So in the second stage, we finally end up with the data frames that only have one animal each. So there are 2 potential problems that people run into when running a group by and apply. The first is that the data from a single group needs to be in one partition, and that's just because the apply function is designed, it's just a Python function that generally is making a pandas call. It doesn't know how to work with data that isn't all there. And the second problem is that shuffles can be slow. So what can we do about this? Okay, so first of all, if you don't like the shuffle that they're doing, okay, so Matt is asking if the group by shuffle retains the original number of partitions or have one partition for each group or something different. I'd have to check the code. I think it defaults to the same number of partitions that you start with, but I might be lying. In practice, I often don't worry about that, and the reason is because I oftentimes end up shuffling the data myself with set index. And when you set index, then you can sort of determine how many partitions you have. The reason why I often use set index is because oftentimes I know something about the data. So the data that I have is not just like random data where I have no idea where things are. It might be something like stock tickers, in which case I know that each partition has just, is organized by stock ticker. If you understand your data layout, you can call set index and tell Dask that your stuff is already sorted in the set, and the set index will be incredibly fast. There are not that many other options, unfortunately, for applies. You can get your upstream data providers to sort the data for you. Like I said, it is great if your data is sorted in a way that matches how you're going to use it. I also think it's a really good idea in general to possibly store your data in multiple formats that sort of match how you're going to use it. You can think of that as building indexes. The last 2 steps, I'm not really happy. The last 2 options, I'm not really happy with, but sometimes you don't have any other choice. You can get creative and implement your operation with apply, concatenation, apply again, which is, say, the same algorithm that we went through for the aggregation. So what's an example of that? So one of the examples that I cited was grouping by a single field and then sorting by value and taking the top 3. If we look at the aggregation workflow that we looked at, you can imagine at each step taking the top 3, then taking the top 3 again, and then taking the top 3, because that taking the top 3 step is a reduction. It doesn't reduce to a single row, but it reduces to 3 rows, which is oftentimes a lot smaller than your original data set. And if you do that, then the operation can actually be broken up into multiple steps with data reductions at each step. The next option is you can also get creative and re-implement your operation with map partitions. So let's take another common example, which is z-scoring. So I want to take all the data for a single group. I want to compute the mean and the standard deviation, and then I want to subtract the mean and divide by the standard deviation. So computing the mean by group is a pretty simple group by aggregation. Computing the standard deviation per group is also a pretty simple group by aggregation. And once I have that information, I can use map partitions, pass that data in, assuming it's not super big, and then just demean every row by the appropriate value and divide it by the appropriate value. The last thing that I wanted to cover are just sort of general tips, because I realized that when I was writing this presentation, I went through specific things to pandas group bys, but there's also a lot of things that you can do on the Dask DataFrame side that will make your life easier, which are not specific to Dask DataFrame Group bys, but will help you with Dask DataFrame Group bys. The first one is that you can optimize your memory. The pandas string type is oftentimes more efficient than the objects that you normally get with pandas strings. So it's a good idea to convert to the new pandas string type. It's also a good idea to use categoricals. In the slide, I say maybe, and the reason I say maybe is because that's not always true. A categorical, when you think about what a categorical is, a categorical is going from a set of distinct strings, they're almost always strings, I think, strings, and converting that to an integer. And so the memory savings that you get are converting from very long strings to encoding them as integers. But the trade-off is that every data frame needs to retain all the unique values, right, in order to be able to map from the integer back to the original string value. So categoricals are good if the strings are very big and you have very few of them, right? So just for some intuition, like what's the worst case scenario for categoricals? If every single row is a new unique value. So if the number of unique values is the same as the number of rows, categoricals are terrible. What's the best case? The best case for categorical is if I have one value and it's a gigantic string. I guess that won't help it much. Let's say, oh no, well, if I have one value and it's a gigantic string, then the categorical is amazing. Last, and I think this goes without saying, but oftentimes we forget, drop columns you don't need before you do expensive operations. The next thing that I would recommend is the repartition. I often used to skip this step because like my old workflow was like I would just do stuff and then troubleshoot problems as they occur. But most people are consuming data produced by other systems, and a lot of those other systems are messy and they produce partitions that are crazy. So some partitions are gigantic, some partitions are tiny. Repartitioning your data so that they're kind of uniform and like of reasonable sizes is generally a good thing to start with. I mean, if you know for sure that your partitions are reasonable, then you don't need to do that. But if you don't, it's definitely worth looking into, or just repartitioning to make sure that it looks good. Finally, prioritize any reductions before you go into your group by or shuffle, right? This is similar to dropping columns. Like just if you can reduce data, do any filtering beforehand, do that. And finally, I'll say this again, sorted data is your friend. Ideally, your data sources are already sorted in a way that maps with how you use it. If you're working with time series data, maybe you can get your data sorted by time. If you're working with stock tickers, maybe you can get your data sorted by stock ticker. Yeah, that's the ideal case. So thank you very much. My name is Hugo. That's my Twitter. You can talk to me there. I'm happy to take any questions. I don't see any in the Zoom chat, so maybe there are none, but if there are more, I'm happy to take them.
Awesome. Thank you so much. Thanks, Hugo.
Okay.
I think we're also at time. So I think I'll stop recording now and we can move on to the next one.